Alright guys, so as you all know, the midterm is tomorrow. So today's problem session I'm going to go over last year's midterm. You should all have it on the website, so hopefully taking a look at it. And I'll go pretty quickly through it, and at the end I could answer any questions you have and also maybe present a little bit more material just to make things more clear. Okay. Yeah, the midterm tomorrow is going to be in class, so it's those tests. Alright, any questions before we start? Okay.
No problem. Can we bring like other books to the exam? So
You can bring whatever books you want.
Oh yeah.
Yeah. Gelb and Vandervelde, whatever. Khalil, anything. Probably won't help you. Okay, so number 1 on this test. So it says consider the feedback system with linear element L and nonlinear element. So pretty standard. And he gave you the Bode plots for these things, and so often this is pretty common because I mean, this way he could give you a Bode plot of some really complicated system without you having to draw it on your own and make all sorts of mistakes and stuff. So the Bode plots look like this. So the magnitude of L, like that. This is 1. Something like that. Phase looks like so. It looks like it goes through negative 100. It starts from 0, and it goes down to 180. And the plot of the nonlinear element was also provided, so that looks like this. So the first thing you notice is that the phase of the nonlinear part is negative 90 degrees. So this is something that we haven't really seen in our examples, and makes it just a little bit more interesting. So the first part asks what are the frequency and amplitude of the limit cycle. So with this type of question, the general approach is to go the graphical method and draw the Nichols plot. So we have Nichols diagram. So it's 90, and the linear element, it starts from here and then it goes down to 180. So that looks something like this. Right? For a nonlinear element, so we know that the phase of n is negative 90 degrees. So what's the phase of 1 over n? Anyone?
Negative 90.
Negative 90 or 90?
Negative 1 over n.
1 over n. Right. So it's actually positive 90 because let's say your n is some complex number, right? That's like got a magnitude and it's got a phase, right? If you take 1 over this, right, you get 1 over the magnitude and then 1 over the phase, right? This part is e to negative j theta. So do you see how, like from 90 degrees, you come down and it's now shifted by 180 because of that negative sign. So the phase of 1 over n is plus 90. Now we do the phase of negative over 1 over n. And again, you do it 180 degrees, so it goes back to negative 90. Right, does everyone see this? So, how about the magnitude? So, 1 over n, when n is really small, 1 over n, when n is 0, 1 over n is infinite. So as we increase a, the magnitude of 1 over n drops. So we start from way up here, and then you go down as we increase it. Okay. So where does it intersect? Well, that's when the linear part crosses the 90-degree mark. And if you look at the Bode plot, it's approximately 1. Right? And the magnitude of that point is it's approximately 1. So at omega equals 1. Approximations are okay during the test. So we have the magnitude of 1 over n equals the magnitude of L equals to 1, which means that the magnitude of n we want is 1, and just label this. So when this is 1, over here we get approximately 1.4. So the amplitude of our limit cycle is approximately 1.4. And I think that's the first part. Frequency and amplitude. And frequency. Any questions? Okay, part B asks, is the limit cycle stable? So for this, you could do a simple analysis and draw a Nyquist plot. So you could draw a Nyquist plot of L and then draw the Nyquist plot of 1 over n and then see if it connects. So if we do that for L, we see that it starts at a phase of 0 and magnitude of 1, and then it comes down to 180. So it does something like this. Oops. All right. Yeah. Okay. And our 1 over n. So that's negative 90. So that comes up from negative 90 and does this. Okay. So here, this point is our limit cycle. Now, the analysis we said in class was when you increase A, if it becomes encircled by the Nyquist plot, right? That means, so when A increases, 1 over N decreases because this is the magnitude of 1 over N, it's now decreasing. So the magnitude of N increases, and the magnitude of NL increases. And if we're just on the point of neutral stability, and we increase NL, then that makes the Nyquist plot of NL larger, and it's going to encircle the native 1 point. Let me just draw, let's see, just make that a little bit more obvious. So if we draw the Nyquist plot of NL, okay, that's going to look something similar, except it's going to be shifted by 90 degrees. Okay? I'm going to draw NL. So this is just for L. So that's going to look, it's going to, okay, so if we shift the plot of L by 90 degrees, we get, because of the phase of N, we get plot of NL, which looks something like this. And the limit cycle happens at the point of neutral stability, so right here, right, it just barely touches the native 1 point. So if NL gets bigger, right, when A increases, then this whole plot is going to get bigger, and it's going to encircle the native 1 point. Right. And that means when you do the Nyquist criterion, so this is the number of unstable poles of the open loop system, the number of clockwise encirclements about the native 1 point, and this is the number of closed loop unstable poles. So if P is 0, and now you have your N, right? If your N is 1 now, then your system's going to be unstable. So that's the basic intuition behind this analysis. That if it goes in and it's encircled, then it's unstable. Later on, if we have time, I'll show you a case where this gets a little bit more complicated. But for now, this analysis holds. So remember the Nyquist criterion. It'll be important. So it's unstable. Any questions? Is this clear? Okay. I think that's it for number 1. Number 2. So number 2 says, consider the closed loop system, and it represents a bang-off bang control. So we have a closed loop system with a dead bang. And our G of S is 1 over S and S plus B. So now we need to sketch the phase trajectories of this plant. So there's 3 regions. One is when U could be, when U is, this is U right here. when u is positive m, when u is negative m, and when u is 0 in the deadband region. So how do we do this? Well, first note the equation of motion that's given plus bx dot equals to u. So this is a plan right here, right? So we could manipulate it and get into our usual kind of slope type form, and then we can apply the method of isopods. So we can do x double dot equals to u minus bx dot. X double dot is also x dot dx dot dx. And we have so here's the equation for a slope. Let's go to the phase plane. So we have, so for this first part, we're going to have to draw kind of 3 phase portraits. The easiest one, let's just look at when u is 0. Okay. Then this part is gone, the x dots cancel out, and our slope is just minus b. So that's pretty straightforward. X dot, they just look like so just whoops. Sorry. So they stop along the x-axis. Okay. That one's pretty easy. How about let's have u equals to plus m. Our dx dot dx is going to be m minus dx dot over x dot. So now notice that if so, let's do it this way. So if I'm looking for a line of 0 slope, right? We can see that this happens when x dot equals to m over b. Right? And so that's going to be a horizontal line, right? Or x dot equals to m over b. So now what happens if x dot gets really large? So like in these regions far away. Well then x dot is going to be, so this term is going to be much larger than the m. So this part kind of becomes irrelevant, and our slope, it becomes essentially negative b. So that means if we're up here or down here, right, our slope is negative b. So And you can see that on the line x dot equals 0, it's infinite, right? So it's vertical. Yeah. So if you do a little bit more of these things, I'm not going to go into it because it becomes tedious. You end up with trajectory set. Look like this. And the bottom ones, they come up and they go like that. So you could do a similar analysis with u equals to negative m, and you'll end up with, first of all, negative m over b, and your trajectories are going to look like this. So now let's put in deadband. The deadband is going to separate our region into 3 sections. Or here we have u equals to negative m. Here we got equals to positive m, and u is 0. So when we're down here, when we're over here, we're going to see trajectories that look like this. When we're here, trajectories that are like that. And when we're in the middle, we're going to have trajectories that are like this. So that was part B, sketch the complete phase portrait. That would do. So part C, in what range of the state space can the system come to rest? So here we could see pretty clearly that it's D, it's negative D. That if the system stops anywhere along this line between x is negative d and x is d, then once it gets to this point, your velocity is 0. You're getting pushed from both sides. It's going to stop. Right? So the answer is just all along here. Part D says, let's put in some numbers, and we're going to have B is 1, M is 1, D is 1. And what is the maximum number of control switches that can occur before the system comes to rest? Sketch an example on your phase portrait. So we got 1 here. Our m over b, this becomes negative 1. Over here, it becomes plus 1. That's how you need it. And our slopes over here, right, becomes slope of negative 1. So let's say we're coming really, really far away. We're coming down here. Let's say we're on this side, right? I'm gonna come down like that. Okay. So the first thing that's gonna happen, we're gonna have it's coming down. It gets to this point, right? You know, it's way up there. It switches once, right? And then it follows this -1 trajectory to here, switches twice, right? Now it's going to follow this curve. It's going to come down like this. It's going to get to here, switches for a third time, and that's it, right? So you can show to yourself that it doesn't matter where you start, you're going to have 3 switches and you're going to stop. Moreover, if you, right, the further away you're coming, the more this point over here is -1, you're going to follow this trajectory straight to the origin. So that's number 2. Any questions? So number 3 is about describing functions and dither. So it says given the system shown in the block diagram says so we're driving some force output with a force command, but so let's see. Yeah, but over here our derivative is can only be controlled by a bang actuator. So we're trying to track. In part A it says assume that there's no dither signal and derive an expression for the closed loop transfer function f/fc. And does the amplitude depend on the command? So the first thing, we're going to assume there's no dither. So this is a sinusoidal function. Right? So we can approximate this ideal relay by its describing function. We call it NA, where NA is 4m/πa. So we can call this E and we call this X, where the magnitude of X, right, is the amplitude that's going to our nonlinearity. So to find the transfer function from fc to f, first we need to figure out what A is, right? Because that's gonna, everything's gonna depend on A. So we gotta figure out what A is in terms of some other known quantities. So the first thing we want to do is find the transfer function between FC and X. So let's do that. Okay. Just gonna write it out. X equals to KE. Our E is FC minus F. But F is this stuff, so it's FC minus 1 over S 4M over pi A plus K. That's E. So E over C is 1 over 1 plus 4 over pi A plus K. So X over C is, can move the S around, so I get KS over S plus 4 So it says in the problem, in class, Professor Rock suggested you find A by iterating, doing so for a bunch of A's. Here we're trying to find a closed form expression for A. So we could say that the magnitude of X is A. So we have A equals to magnitude of all of this. At S equals to J omega. And now it comes a little bit of algebra. It's not great. So what we could do is I'm going to move this over. So if I sub that in. So these are these are complex numbers. I can square everything, and by squaring I mean taking the magnitude squared, which is multiplying the complex number by its complex conjugate. Right? So I get omega squared plus 4k over e squared. So now we can move things around and won't go into it. Your final expression for A is going to be EC at this level. It's going to be K over omega. FC squared omega squared minus 4m over pi squared square root. So you basically multiply this out and move everything to the other side. That's it. So from this, you can see that A depends on both FC and omega. So now we have A, we can find what we're asked to find, which is F over FC. And that's just K for so we can substitute our A's into here. And I won't write it out, but you could see that the expression will depend on both FC and omega. Interesting though, if you do sub this into here, you'll see that there's a K up here on the A, and there's K, so the K's cancel, and the final expression, this expression, doesn't actually depend on K. Okay. And that makes sense, because it doesn't matter what K is, it gets washed out in your relay.
So the reason we didn't really have to iterate, like compared to that like homework problem we did, it's because we could kind of find the analytic expression.
Yeah, you can find that. Yeah. So in this case, it's a little bit hairy over here, but doable.
And we have to find the magnitude of A, because
well, A is the magnitude of X, right? That signal. So A is just a number. Okay. So that was part A. In part B, you add the dither signal. So we add the dither signal, and we want to again derive the closed loop transfer function, and it asks, does it depend on FC? We're assuming that omega d and the big D are big enough to make the ID-IDF assumption valid. So what that means is omega d is much faster than omega, right? And fast enough to make this input look like a constant, right? So here again we're looking at the transfer function between our actual input FC to F. We're not looking at the dither, we're just assuming it's there, right? It's doing its thing. So we can, when we look at this, this is now like the low frequency stuff, right? The low frequency stuff can be approximated over here by our NP. So the dither is there, but compared to the dither, our input looks just like a gain. So we can do this. So NB is just 2M over. It also says in the question that we can approximate A as KD. So why can we do that? So this approximation comes from, so A is here, right? So A is actually K times, this plus this minus that. by making that assumption, we're kind of assuming that D, first of all, is much bigger than FC, and also D is much bigger than whatever roll-off we get when it comes back. So, I mean, depending on what the plan is, sometimes it's a good assumption, sometimes it isn't. For the exam, we're going to assume that. So we can sub that in, and our NB becomes just 2m over HD. So if I just clean up a little bit and look at what we're really analyzing, what we're saying is this. And now it becomes straightforward. So when you multiply this by that, the k's cancel out, and you end up with this. And it turns out that this, when you're making this assumption and adding dither, it does not depend on FC or omega. And that's it. Any questions on that? Still got a little bit of time. Alright, good. So first I'm going to ask, is there any general questions about any of the material?
Oh yes, and how you got to that NB?
The NB? So we're saying we have our dither signal, it's there, right? It's much, much faster than this. So compared to our dither, this looks like a gain, and over here, our x, right? This looks just like b plus a cos omega dt, right? So this part looks kind of like gain. So when we're analyzing the low frequency part of it, right, we can just replace our relay with NB, right? And NB is this, but in the question it says we can approximate A as K times D. So I'm just subbing it in.
Are we going to be given all the NDs and NAs for the relays?
I think so. I think all the describing functions that you need will be given to you, but it's, I mean, remembering these two is pretty easy, so I'll just do that. Yes?
So are we not using the NA term because it asks for F over FC?
Yeah, we're not using the NA term because that's dealing with the dither itself. We're just kind of assuming it's there.
But that does exist in response, right?
There does, sorry?
Like that isn't, it's not gone.
No, it's not gone. It's like
We just want us to address it.
yeah, we're just not addressing it. Another part of, we could also draw the system as, you know, we got our D equals omega dt over here, and then K and A. Right. So this exists, right? If we're trying to design D, for instance, or trying to figure out what these are, then we would have to use NA. But since we're only looking at the low frequency stuff.
We can use superposition because there's the ID-IDF assumption.
Yeah, so the ID-IDF assumptions allows us to use this because we're working at the different frequency ranges. And remember what the condition was, that A is at least 3 times RB, and omega D is at least 3 times our other omega here.
So FC we just pretend is like 0 when we look at the high frequency one, since it's like just probabilities.
Yeah, it's a constant compared to this, right? So, I mean, remember when we're doing our NA, and NA is a sinusoidal input describing function, right? So if we have a constant DC, then nothing happens here. It's a relay. Okay. So in the last couple minutes, I want to.
Can I just sorry, one more quick question on this.
Yes.
I don't have the test with me. But
Yeah.
it sort of asks, does the transfer function depend on the amplitude or the frequency? And so for the second one, it's no.
Yeah. So for the second one, it doesn't depend on.
Okay. So and the frequency they're asking is the inside the FC cosine omega. Or is
So
that?
the
Oh wait. Oh, I guess it.
so part B just says, does it depend on the amplitude of FC?
Okay.
So over here,
sorry.
A depends on FC, right? But
Okay.
here it doesn't.
Okay.
And also, just to use describing functions in general, we need to assume certain things about the roll-off, right?
Yeah.
And this system probably doesn't satisfy that.
In this system, probably it's not a very good assumption.
Okay.
But because in the midterm we're trying to simplify things. Yeah.
Okay.
So yeah, the roll-off is very important. I want to go over the Nyquist stuff a little bit more, just to make it give you guys an example of a case where you got to be more careful what you do. And this comes from the midterm a couple years ago. So it says, so we have some kind of plant that looks like this. It's got this inner loop, and it's got, this is U, this is AC, and this is D. So the first part of this question wants you to write this. There's a delta 1, there's a delta 2 here. The first part of the question wants you to write this system in terms of an N and an L. You can just do that as an exercise. But basically, once you've done that,
move the KB plus KBS back?
Sorry?
Can you just move that back?
Yeah, there's a number of ways you can do it. I mean, I personally would just do
G
the
is
actual
linear?
algebra to do it. Sorry?
G is linear.
Oh, G is a constant.
Oh.
Yeah, let's just say G is just a gain. Anyway, when you do this, so I'm gonna call this X, I'm gonna call this Y. This is our nonlinear part, right? So, so our L, I'm gonna say is so this is the input negative X over Y. So the first part wasn't, I mean, you could do it by yourself, that wasn't the main point of this question. But let's say our L is this. And in the second part of the question, he gave you Bode plots for what? Of N and L. So we're looking at something like this. And then L looks up to negative 90. Okay. So if you draw the Nichols diagram for this, the Nichols diagram is going to look like this. And our nonlinear part, right? The phase of that is 0, right? So the phase of negative 1 over n is just negative 180, and you can show that. Well, if you just look at this, then you can say that it does something like this. Right? So n starts off at 0. So 1 over n is infinite, goes down, comes back up. So there's a couple points where they intersect, and that's going to be your limit cycle. So the question asks you which of these two limit cycles are stable. And I mean, well, you know, for each limit cycle, are they stable or unstable? So for the first part, so for a question like this, again, you go to the Nyquist plot. And if you draw the Nyquist plot, it's gonna look something like, we'll start off at minus 270. It's going to come in like this. And do that. So that's half of it, and the other half is this. But recall what L was. L was right. It's got 3 poles at the orbit. So if I'm on the complex, on the root locus kind of thing now, where this is real and imaginary, right? When we do our Nyquist, we gotta, go up this way, and then here at the 0, you gotta kind of go around these 3 poles, and then keep going, right? So it turns out, if we do that, if we're looking at this point right here, what is the phase of that, right? So this is so negative 90 degrees, but because it's a pole, it's positive 90 degrees, right? And there's 3 of them, so it's positive 270. So we're here, right? So now we're moving along this curve, and let's say we're over here, right? Each of these has got a negative 45 degrees. Because it's a pole, it's positive 45 degrees. And multiply that by 3, we get positive 135 degrees. Right? So when we're out at infinity, we're coming over to here. Right? Here we got 0, right? So it goes to 0. Here we're at negative 135 degrees. So that's that. And finally, we're at here. Okay. So this is the full Nyquist plot for L. If we draw our n, right, it's at negative 180, so it comes over like this, and then it comes back out. Right? So this is negative 1 over n. So if you didn't draw the full thing, you might be tempted to say, well, for this one, as I'm increasing a, I'm inside, so it must be unstable. But if you did the full Nyquist, you'll see that here we have a counterclockwise encirclement, and out here we have a clockwise encirclement. So n in this region, well, n as in like z equals to n plus p. So not your nonlinear thing, but the number of encirclements is actually 0 in here. And now here, it's actually 2, because you got 1 and you got 2. So it turns out that this first limit cycle, in which when you increase a, it goes in. So this first one is actually stable, and the second one is unstable. You see that? Another way to say it is, over here, if I increase n, say I'm on the first one, a increases, my magnitude of 1 over n decreases, n increases, and L increases. However, so NL increases, but if we draw the Bode plot, the Nyquist plot of NL,